Curious George has escaped again. The man with the yellow hat spots him hanging from a tree limb. He raises a rifle loaded with a tranquilizer dart, points it directly at George. When he fires, the sound startles the ape, who then at that same instant releases from the branch and drops. What happens? Now, we know that the bullet doesn't move in a straight line, so that if George had stayed where he was, the bullet's actual trajectory will be a parabola. It will be in free fall. So it's going to pass somewhere below George if he had stayed still. But George drops. So the question is, when George lets go and starts to fall, does the bullet pass underneath him? Does George drop so far that it goes above him? Or does the man in the yellow hat hit his mark? Do we have enough information to figure it out? Let's say we know the launch speed from the rifle, the distance, horizontal distance from the rifle to the position right underneath George. We know George's height above the top of the rifle. And if we know these two distances here, I guess we also know this angle. Note that this blue triangle and this big green triangle here are similar. They share an angle here and they're both right triangles. Therefore, we could say that tangent of that angle could be written as v1y over vx, but it's also equal to, tangent of this angle is this height over this distance, h over d. We'll use that fact later on. So if we know the angle, then we also know the two components of our initial velocity here. We know that vx is the speed times cosine of that angle, and v1y is the speed times the sine of that angle. Okay, knowing all this information, can we figure out, does George get shot or not? First thing we can, so the first step in this process is to figure out when the bullet reaches event 2. We'll call event 2 here the moment when the bullet passes through this line, dropping directly down from George. So when the bullet passes this point, we'll call that event 2. So how long does that take? How much time passes from when the bullet launches to here? Remember that the monkey drops at the same time that the bullet launches. So they're both moving simultaneously. Okay, how long does it take the bullet to get here? We can figure that out by going to our equations. And we want to know about the horizontal movement of the bullet, so we're going for this equation right here. Figure out the time it takes for the bullet to travel this horizontal distance, and we know its speed in the horizontal direction, vx. So there's our equation. We know our change in x is d, and vx can be written like from this expression here. And then there's our delta t. We're going to rearrange algebraically to solve for that. And this will be an expression for the time. Okay, so if we know the d and the speed and the angle, we can figure out how long it's going to take the bullet to reach here. Next question. How high is the bullet at event 2? What is its vertical position here? We call this y2 right here. What's the height of the bullet when it reaches this point? We know how long it took to get there, so now we can go to the vertical equation. We know the time that it was traveling. We can figure out the change in the bullet's height. Oh, did I keep saying do I keep saying bullet? It's definitely a tranquilizer dart. Yeah, tranquilizer dart, sure. So we can figure out delta y. So starting with this equation, we know the initial speed of, the y component of the initial velocity, v1 sine theta. For delta t here and here, a change in time, we can use this expression right here. This tells us how long it took the bullet to reach that point, so we can put that in for the time here and here. When we put that expression in right here, we've got to square the whole thing. And then our change in y will be y2 minus y1. y1, of course, is going to be 0. We'll define this to be a height of 0 where the bullet starts. So y2 minus y1. Okay, now I'm going to simplify this expression, this term right here. I've got v1 over v1. Those speeds cancel out. And I've got sine theta over cosine theta. Time to pull out of my hat another handy trigonometric identity. Sine theta over cosine theta by this argument is equal to tangent theta. So I can replace sine theta over cosine theta with tan theta right there. So this term I've just brought down, that hasn't changed. Now d times tangent theta. Here's the key to the whole problem. These two triangles, remember, the blue one for the velocity and this big green one here for the distances, those two triangles are similar. Therefore, tangent of theta can be written as the height over this distance, h over d. I'm going to put h over d in for tan theta right here. So if I put in h over d right there, d cancels d, and this term here just becomes the height h, leaving me with this. This is the answer we were looking for. This tells us how high the bullet will be when it reaches that spot right underneath George. So it depends on George's height and depends on the initial speed of the bullet, the angle, and that distance, d. Okay, we're going to come back to this expression later. Now we know this height, where the bullet is at the moment it passes underneath George or possibly above George, depending on where George is. So the last piece of the puzzle is, where is George located when the bullet reaches event 2? Is he George above it, below it, or right at it? So where is George at that time? Well, we need to know the change in his vertical position, so we're going to use this equation once again. So this is going to be George's change in y. His initial velocity, well, when he releases from the branch, he doesn't push himself downwards or upwards, so he starts from rest. So the initial velocity is 0. That whole term drops out, and we just have this term. So his change in his vertical position, final minus initial, we'll call his final position, that is at the time when the bullet reaches here. So his position at that time, we'll call it yg for the vertical position of George. That's his final position minus his initial position, which is h. He starts up at this height here, h. That's his initial vertical position. So final minus initial equals, that term is 0. And then here, for the time, delta t, I'm going to put in this expression that we came up with earlier, the time it takes for the bullet to reach here. Because the bullet and George have been traveling, the time it takes for the bullet to reach here. Because the bullet and George have been traveling for the same amount of time. So I'm putting this expression in for time right here. Okay, there it is. I got to square the whole thing. Now, to solve for yg, I'm just going to move this h over to the right-hand side. And the height of George is h minus this whole term here. Box this thing. That's the expression for the height of George when the bullet reaches that spot, compared to this expression for the height of the bullet at that same time. Let's look at them right next to each other. Here's where the bullet's located. Here's where George is located. Notice the expressions are identical. They're going to be located at the same exact spot. Therefore, conclusion is that the bullet's path, although it curves downwards, George drops at exactly the right rate, so that as the bullet moves, they intersect and we have a hit. And it doesn't depend on what the angle is, or d, or the h here. As long as George drops at the same moment that the bullet is fired, you guarantee that they're going to intersect right there. George lived to tell the tale of that day, but never forgot the insult done to him by his human master, which is why he grew up to become a pro-ape, a handsome pro-ape revolutionary.